The Rosetta orbiter has begun its science already in May 2014. This period of science investigation will last right the way through to the end of 2015, after it's passed through perihelion, the closest approach to the sun. The lander will be deployed in November and hopefully last up to about March in 2015. So that's the window of opportunity for doing science there. Together, they'll amass an amazing amount of information for us.
In fact, I was waiting this day for more than 10 years. I launched Rosetta in March 2004, and it has been a very, very difficult launch because we had to postpone the launch, we had many reports and so on, many delays. And since the 2nd of March 2004, I was waiting for this day, and today we are on Rosetta. We still have some excitement in front of us because we are going to land on the 11th of November, but already it's very, very exciting to have Rosetta very close to the comet.
Kometen sind für das Leben möglicherweise, und das wird.
Comets could be important for life on Earth for two reasons, and Rosetta will tell us more about these. First of all, we think that comets brought water to the Earth. Without water, there is no life, at least not the forms of life that we know. Secondly, and this is more like science fiction, comets could have brought the basic building blocks into this turbulent disk which formed the Earth.
Die sind also schon mit Kometen auf die Erde gekommen.
So, after Philae has landed, we will see if it finds these amino acids. Philae will drill and analyze the findings in a small laboratory, an automated laboratory, which will hopefully help to answer one of these very important questions.
With the Rosetta mission, we're trying to find out how our solar system was formed out of a huge dust cloud around 4.6 billion years ago, and how life on Earth became possible. Comets are the unchanged residue of this dust cloud. In February 2014, Rosetta was activated more than 8,000 million kilometers from Earth in order to chase Comet 67P, an object of dust and ice the size of Mont Blanc, to intercept it and finally accompany it for a year in the inner solar system. The Rosetta orbiter and the Philae lander contain 21 instruments with which the comet will be measured in detail, sampled and analyzed. Rosetta has already supplied many images and preliminary data from other comets on the way to Churyumov-Gerasimenko. But after landing, we'll learn more about the original composition of the comets that were striking Earth, hopefully giving us long-awaited evidence of where we come from.
When I heard about this project for the first time, I simply responded with incredible and not feasible, but we've made it. We are now close enough to this comet to examine it and hopefully learn how our solar system formed and what the future of our solar system will look like.
A fascinating and unique aspect of Rosetta is that we had to do these number of flybys. We had to go past the Earth and use the gravitational acceleration of the Earth and also Mars to pull us out into the same orbit as the target comet Churyumov-Gerasimenko, and that took 10 years.
Well, this is sensational. The moon landing was, of course, a highlight for human spaceflight, and Rosetta is a highlight for robotic spaceflight. One has to say it would be unrealistic for us to fly a man to such a comet. 67P is so far away from our planet, and Rosetta itself had a mass of 3 tons. Even a launcher like Ariane 5 failed to give it the necessary speed. Rosetta had 3 flybys past Earth and 1 past Mars, which gave it enough speed to get to the comet. So manned spaceflight into such regions, it is still out of the question. Nevertheless, I must say it is a great moment to witness all this. We have achieved our goal, reaching the comet, and to now fly in formation with it. In November, the landing will take place. Unique in the history of mankind. It's fantastic.
This is another demonstration that 20 countries of Europe can work together and make what nobody else has done in the world, meaning that it's 50 years of cooperation, but 50 years of innovation. I think that Today we are the first around, at the rendezvous of a comet, but we were the first to provide the fossil light after the Big Bang. We were the first to land on Titan. So it's a series of firsts that we have done, and not only ESA, because it's thanks also to industry. It's thanks to the scientific laboratories, but the momentum is provided by the member states, which are really willing to show what they can do when they are joining forces. So this is the Europe that I like.
In 1957, the race began between several nations for supremacy in space. Sputnik sent out the first radio signals. Yuri Gagarin was the first man in space, and John F. Kennedy announced America's plans for the first moon landing. At this high point of the Cold War, the two European physicists, Pierre Auger and Eduardo Amaldi, postulated that rockets and satellites should only be used for science and not for saber-rattling.
First, CERN was created in 1955, 10 years after the end of the war, and a few years later, after the launch of Sputnik 1, the Europeans decided to create a European Space Research Organization to go to space and follow on and be part of the quest of knowledge that space was opening to the scientists. So at the beginning, we did not know how to do these things. So we cooperated first with the Americans, who were very happy to cooperate with us, not only because they are very generous, but in this way they could control what we were doing.
Under the leadership of Auger and Amaldi, two European organizations were formed: ELDO to develop rockets and ESRO for space science. The first years were marked by limited budgets, failures with the European launch vehicle, and tensions between England and France.
Then in the late 60s, they began to say, okay, we should really begin to fuse these two organizations. This went in fits and starts, though. And a program was hammered out in a very, very tense meeting in '73, which would be the basis of this new single organization. It would have space science as a mandatory program. Mandatory not because people loved science, but precisely because they didn't want to fund it.
Mandating the member states to pay specific quotas was considered a stroke of genius, as this enabled the success of ESA at all levels. Nevertheless, Europe desperately needed its own launcher.
The Germans were against the development of Ariane. The Brits were extremely hostile to the development of Ariane. It took the French to say, we're going to do this. And it's frankly thanks to French gaullism and a suspicion of the United States' motives that the French embarked on that. And that is undoubtedly the greatest success of European space effort.
In 1979, Ariane 1 was successfully launched for the first time in Kourou. Only planned for the booming telecommunications sector, Ariane was also then used for scientific missions, such as Giotto in 1986. A decade later, ESA suffered its first blow. On its first mission, the brand new Ariane 5 was supposed to transport valuable cluster satellites into space, but exploded just 40 seconds after launch.
n'oublierai jamais dans ma vie de voir ces espèces de géants qui étaient.
I never forget seeing these kinds of giants, project managers, big guys, real bosses who were crying in a little hangar behind the rocket control center. And I swore that we would relaunch the cluster mission, and that's what we did.
The ESA-NASA cluster satellites still operate successfully. The Saturn project, Cassini-Huygens, was also the result of another groundbreaking collaboration between the two organizations.
In 1980, when the situation with the American cooperation was not so good, we decided to build an independent program. We had all the intellectual power to build a good program, but we had not enough money, so we had to be modest. Ambitious and modest.
Before ESA and NASA achieved greatness together, Giotto was the first single European probe. It was sent into space in 1985 to study Halle's comet. The mission followed two German-US probes of the Helios program. Giotto flew past Halle and provided the best ever data and images of a comet. Giotto is regarded as a model for the Rosetta mission. These successes were the precursors of further successful missions, such as the X-ray telescope Newton for studying energy processes in the universe, and the Gaia spacecraft to accurately map our solar system. ESA, however, has long been concerned with the observation of Earth from a close orbit.
We've
cooperated with the EU to launch the first satellite in March of this year for a new observation system. Similar to meteorology, we now observe the environment. We call it Copernicus, and in the next 2 or 3 years, we will launch even more satellites so that we have the first generation of observation platforms in space, from which we will observe many conditions, such as ice coverage, the composition of the atmosphere, the ocean currents, or the pollution of the coastlines. So a large amount of data that is constantly needed and will be available to everyone.
Science was one of the first elements of unification, of intellectual unification and scientific effort, opening the dialogue among very strongly warring nations before, a few years before. And I think in the present context of today, where the world is really changing, we have wars here and there. I think the language of science is the one which will, in the future, make it possible that we continue to survive on our planet.
5, 4, 3, 2, 1, 0. We have ignition.
"50 years of space exploration have achieved a level of technology that put the Soyuz, the Space Shuttle and the Ariane rockets safely into orbit. While the astronauts are brought to the International Space Station by the Soyuz, the Ariane 5 is the most powerful European launcher today and transports payloads up to 21 tons into orbit. Airbus Defence and Space in Munich assembles the rockets and then delivers them to Ariane Space. After only 6 hours travel time from the Baikonur Cosmodrome in Kazakhstan, the landing unit docks with the International Space Station. The ISS is the largest technology project ever, an outpost of humanity in space, 416 kilometers above the Earth. This requires the highest technological reliability, because repairs in space are impossible.
Generally, satellites cannot be repaired in space. There are a few exceptions. The Hubble Space Telescope was such an exception. But as we have also seen with the Hubble, it was highly expensive. So firstly, the design must take into account whether one wants to repair it. Then there must be a shuttle or other device that flies up to the satellite to do the repairs.
The Hubble telescope was designed to receive maintenance in orbit. A total of 5 space shuttle missions to repair and upgrade the telescope were completed. The first missions by the astronauts of the Space Shuttle Columbia to make a correction of the primary mirror and to exchange a solar sail costing 22 million euros were unplanned. The old, slightly damaged sails were brought back to Earth in parts and examined. The most complex operation was the expansion of the Hubble control module. For this, the telescope was completely shut down for the first time since its deployment in space in 1990. This was during the 4th servicing mission to Hubble at an altitude of 560 kilometers. At the time, Columbia had spare parts worth around 200 million euros on board. In the last servicing mission to date, in 2009, comprehensive measures for upgrading and life extension were taken to ensure the operation of the expensive telescope until at least 2018.
And these are incredibly expensive missions. That's why it's not affordable for satellites, and we have to do the extensive testing on the ground.
Spaceflight requires robust and reliable systems that flawlessly support complex missions over 15 to 20 years. This means that even today, we're still using obsolete but proven technology which has to withstand every possible test on Earth to survive in the extremely hostile environment of outer space.
Here on Earth, it is not possible to simulate a complete space mission, even if it is only a satellite with a lifespan of 15 years, let alone a mission to Mercury or Jupiter. What we can do, and examples can be seen at our facility, is to single out certain points of a mission and to examine the material or a component for a precise instant in a mission. For example, we're testing materials at very low temperatures so that we can simulate the requirements for a new LNG tank in a rocket.
In high-tech laboratories, all components are tested, analyzed and developed to deal with the possible stresses of space, such as extreme temperatures and high-energy radiation. This will provide feedback for the manufacturers of components for space missions and set standards for the continued modification of a probe or a spaceship. Rockets are exposed to extreme vibrations at the start and during flight, but must remain stable. Many of the satellite mechanisms are folded for use in space and have to open reliably later on. During re-entry on manned missions, the temperature of the heat shields reaches well above 1,000 degrees. Satellites also have to withstand extreme temperatures on missions close to the Sun.
It is not only the sun that delivers an enormous thermal flux into the spacecraft. On top of that, we fly over the surface area at very close distance. And Mercury is like a very hot stove that puts thermal load into the spacecraft as well. So we are like in a sandwich, in a squeeze between the sun and Mercury, receiving very high temperature from both sides.
In 2016, the satellite Bepi-Colombo will be flying to Mercury, the closest planet to the Sun. The satellite is wrapped in a 3 mm thick thermal insulation, which is handcrafted from various films of computer-generated patterns in a cleanroom tailor shop. These lightweight protective films cannot be produced by machine and also have to be attached by hand to the satellite, and they will only function in a vacuum.
What you see here is a glass ceramic fabric that is metal coated. There are also titanium foils built in, and all is then sewn together with glass yarn. Here are some eyelets, so-called grommets, manufactured from titanium which has been sewn in. This is a closed system again, so nothing can get out of the isolation.
Satellites are fully stocked with the most sensitive measuring instruments. The insulation layers produced in a clean room also serve as protection against contamination from terrestrial materials that would distort the measurements in space and on other planets. Thus, the design, construction and analysis after testing are factors for the success of these costly missions. High-precision, adjustable engine positioning mechanisms for the electric satellite thrusters, together with an electronic control unit, combine to form the entire steering system of Bepi-Colombo and are the key technologies of a spaceship. The construction of these systems requires about 5 years and must be tested. In the Dutch town of Noordwijk, the engine platform and insulation are finally mounted in the space simulator onto the satellite and prepared for outer space.
The performance of the spacecraft was very well. The radiator behaved exactly as expected. Also, the performance of the multi-layer insulation was as expected. We have, on top of that, identified a few heat leaks that will now allow us to, in fact, design a few modifications. But this is exactly why we do such an important test. And overall, I regard these test results as very positive.
In addition to everyday robotic space missions, manned flights are the exception and require years of precise preparations for the astronauts.
I never planned to become an astronaut. I mean, I knew that it's a very small likelihood, and so as a scientist, I knew the statistics, meaning like, okay, if I try to become an astronaut, it probably won't work out.
The volcanologist has already participated in several scientific expeditions during his studies. They led him to the Antarctic and to volcanoes in Ethiopia, Indonesia, and Guatemala. After 5 years of training, he flew to the International Space Station in 2014 to live and work there for 6 months.
That includes basically 1.5 years basic training, general astronaut training, and then 2.5 to almost 3 years of specific mission training. Basic training was really the general astronaut training. It's kind of like the basic university training that we get when you study at university, which is like a general questions about how spacecraft in general work. We also had to study Russian in order to later get training in Russia. We did a lot of sports. We understood how our experiments will work on station. We tried to get a common understanding of science because we came all from different directions, like we were pilots, engineers, scientists. So it's basically just to get everybody to the same level. And after that, we advanced into mission training. Of course, spaceflight training is not easy. I think that's clear. I mean, for 3.5 years, you have to travel almost every 3 weeks. You fly over the Atlantic, you're in different training locations. You spend about 5% of your time at home. And if so, maybe then just a weekend here or there. So it's a challenge. In the last year or so before the flight, 60 to 70% of all the training you do is for emergency situations, which means like training that you hopefully never use. And so far, we've been lucky on the space station. We never had bad emergencies. But of course, you need to be trained on that. So what we train for is, for example, what do you do if you wake up at 3 o'clock in the night and you realize there's a fire on the space station? Or if there's a rapid depressurization, you lose atmosphere because you had a micrometeorite impact. So these are all things that you need to talk about and train before, because in a situation like that, you don't have time to think what to do. And I know that as from my time as a firefighter, that really in these sorts of situations, you have to rely on muscle memory, things that you've done 100 times and you know exactly what to do at which time.
The highlight of the mission was the ISS spacewalk, accompanied by the NASA astronaut Reed Wiseman, to repair a defective pump in a 6-hour extravehicular activity.
The US spacesuit, the EMU suit, actually has a system called SAFER that allows a return to a space station if I ever lost grip on station and lost my safety rope, my safety wire. I would have a little rescue system. And we actually train how to use that in the virtual reality lab. So I have a 3D glass on, 3D goggles on, and I have a little mock-up. And it's actually hard you have to train it for a while to operate, to actually come back and not miss the station and fly into the blackness of space. Although you have to say it's a very unlikely scenario. It has never happened, and also in order to have this happen, several things would have to go wrong before. So you'd have to lose your safety wire, you have to lose your safety anchor, and you have to lose your grip.
As a scientific space laboratory, the ISS provides various conditions that are unachievable on Earth. In addition to equipment for astronomical and meteorological experiments, the astronauts themselves serve as subjects for studies in space medicine, where mission-related stress plays a role as well. The experiments inside the ISS mainly use permanent microgravity, where physical and biological samples are exposed to the space environment for a longer period of time. In addition, the everyday life of the astronauts on the ISS is subjected to extraordinary living conditions.
And I like to take my towel while I have the shampoo in there and just kind of work it. Because without standing under running water, you kind of need to use the towel a little bit to help get some of the dirt out.
And that's it. Thank you.
There's a great sleeping bag. And what's really cool about it, we can zip it up. And then we have little armholes.
No matter how exhausting and full of hardship a long-term stay is for astronauts on the ISS, all of them talk of one special pleasure: the hours they spend watching our wonderful planet.
I can still remember very well when Alexander Gerst was at the summer school in 2006. He had no idea about space. He was a volcanologist, and he found the topic of space here in Alpbach so interesting that he considered working in this area. It was certainly a motivation for him, and we see the Alpbach Summer School as such. It's just a motivation, an opportunity for young people interested in space to find their future here in terms of their career.
Well, Catherine and I heard about it through the ESA site. Yeah. And then we just talked to our coordinators, I guess.
Yeah, and then just filled out an application on the website. So it was all pretty straightforward.
Yeah, my professor in Advanced Space course told me about this summer course, so that's how I heard about it.
The Alpbach Summer School, founded by John Ortner, is an idea factory and training ground for the European Space Agency. Every year, it enables 60 young scientists and engineers to use the seclusion of the Tyrolean Mountains for in-depth studies on various topics of space research and to create new projects for ESA.
I've been here for more than 30 times, and since a few years I am also the president of the jury, which at the end of the summer school analyzes the projects which have been prepared by the students during the 10 days which they are participating in the summer school. So I am the ultimate judge of the quality of their presentations.
The FFG organises the summer school together with the European Space Agency and its member states. We have a national contact point in each member state, which is the respective space agency. They help us in the preparations and are primarily responsible for the students and financially support them so they can then come to the summer school.
Also die Arbeit, die sie jetzt gerade machen, ist sozusagen die End.
So the work they're doing right now is the final phase of the project. Tonight at midnight, so in less than 11 hours, we have the deadline. They've had the last 1.5 weeks, so to speak, to create the idea behind this mission. This year is about understanding tectonic processes on Venus, because it is one of the few planets in our solar system where you can observe them, which of course also has repercussions over what we on Earth know about plate tectonics.
While future astronauts prepare for a possible return to the Moon with laptops and calculators, the NASA Apollo mission seems like a contemporary document of the distant past. An adventure that originally attracted people to the cinema in 1902, and one that since July 1969 has continued to spur on spacefaring nations to return to sustainable manned missions to the Moon. Success probably lies in a big joint project of the space agencies, almost as a follow-up project of the ISS, with a habitat on the Moon.
It's one small step for man, one giant leap for mankind. Columbia, this is Houston, AOS, over. Houston, Columbia, navigate, over. Roger, the EVA is progressing beautifully. They're setting up the flag now.
Heute ist es, damit wir vorankommen.
For us to move on today, so we can operate something like the International Space Station, we must work together internationally.
The Mir, named after the Russian word for peace, was one of the most important space stations. After the political climate changed, Mir was opened up to Western space agencies. This allowed Franz Fieberg to discover for himself the natural beauty of our home planet.
But when you look down, you see no boundaries and you think, what are people doing? Why are there wars to move boundaries around? Then you are out of this atmosphere, outside of this 100-kilometer shell around the Earth, this bowl surrounding the Earth. And we are at a height of 400 kilometers, where gravity is compensated by another force. If something catastrophic happened to us, we would just fly out into space. That's when you realize humans are actually very insignificant. If you look out into space and experience the vast dimensions of the universe, and then this small, vulnerable Earth, it becomes clear that we are not the most important ones out here.
Even if the Earth is only a small, pale blue dot in the universe, we still want to explore our origins. And that is what the Rosetta mission and the important landing at Comet 67P stand for.
Now we're at the Comet since August 2014. We are currently planning to be in operation up until the end of 2015. We could go further. That's dependent on logistics, basically, how much fuel we've got left, how the instruments are doing, whether we can still do science. There's probably money involved in there as well, because financially that's where we've budgeted to go to. If we consider the Philae lander, once we deploy the lander, it ultimately has a lifetime, once it's on the ground, up till about March next year. And after that time, some of the components will not be able to cope with the temperature that it'll be experiencing on the comet's surface. But at the moment, we are in this prime phase, this window of just over a year of absolute, comet fantasy in terms of science. I think it's true to say already at this date now, we've probably taken more data at a comet than has ever been taken before. And that's a unique aspect of Rosetta already, this rendezvous. The fact that we got into step with the comet, we are in the same orbit around the sun as the comet. Everything else before has been a flyby. It's an epoch in time, a snapshot, and then you go. You're traveling at tens of kilometers a second, hundreds of kilometers away from the body. Rosetta's got into step at 1 meter a second. It's walking pace with the comet for over a year and at very close distances. I think today we're within about 20 kilometers now. So that's the thing, that we see this evolution, and that's what makes it extra special. So we've got loads of data already, but we're going to get more and more data and really unlock. It's going to be this unprecedented characterization of a comet that's never been done before. And as I say, and that gives you this broader picture of the science behind comets, why they're important to us, And what we learn with Rosetta, because at the same time we also have ground-based observations, so we're using ground-based telescopes to look at the target body, Churyumov-Gerasimenko, at the same time Rosetta's there, and you can make this fantastic comparison to what you believe you're seeing from the ground to what we're seeing in situ with Rosetta, and then that application can be transferred to any other comet that we have observed from the ground. It's really giving us this massive leap forward in cometary science.
Criteria for the selection of the landing site were the sunlight and soil conditions. The choice fell on landing site J, on the so-called head of the comet.
The day we will do the landing, we will not know how the comet is behaving on that day. We cannot do weather forecast of the comet, we cannot do activity forecast of the comet. And this is what is posing the highest risk for the whole operation.
Also der wirkliche worst case.
So the real worst-case scenario would be if we send the lander away, and Philae needs 7 hours until it's down on the comet, and in the meantime the comet has one of those gas eruptions. The lander would not make it. It would simply be blown away. But even if this scenario did occur, we would still have the orbiter with its instruments, which could still examine enough to be able to answer many of the substantial questions.
Philae's landing on the comet is unique and will certainly bring us new knowledge. For science, this will be a major step in the further exploration of space.
Anything in space for me is where we should be going. The adventure, it's the excitement, but also science. So yes, we should be going back to the moon. We should be going further. That's how it works. We should be investigating more. We should be pushing science boundaries, technological boundaries.
The curiosity of mankind is one of the main reasons for the great importance of space. During the last 50 years, we have explored the Sun, planets and moons and expanded our knowledge of asteroids and comets. As part of the Apollo program, we visited our moon. Since then, we have learned a great deal about how we could potentially live and work in space. From robots on Mars missions and people aboard the Mir, the Space Shuttle and the International Space Station. More and more countries want to explore space, and private companies will soon carry out flights into orbit. But there are still many unanswered questions. We have just begun to go beyond the edge of our solar system into interstellar space. And the Hubble telescope has captured many pictures of distant objects in the universe. The adventure has just begun.